Okay, well, unless we state otherwise, if we're talking about an arc APB, we will assume it's a minor arc. So it is less than 180 degrees. It's less than a semicircle. We will assume it is a minor arc. That's what that means, a minor arc. And it lies on the half plane determined by the line that goes through the center O and the point A. So notice I drew it like OA is the x-axis. So the arc APB would be, let's see, this arc right here. And remember what the measure of that arc is whatever the measure of that angle is. So now let's look at a theorem, and it says that if we have an arc AXB ending with B, and another arc that begins with B, BYD, if they're two arcs and they only intersect, their overlap is nothing but the point B. And if the arc ABD is equal to the arc AXB plus or unioned with BYD, then what is the measure of the big arc? Well, let's draw the picture. It's really quite simple. Here is the arc AXB right here. And the measure of that arc is whatever that angle is right there. And then the other arc that only shares one point with this, the other arc is BYD. So we have two arcs next to each other that share one single point. And the measure of that second arc would be whatever that angle is. Well, the union of the two of them is this one great big arc, ABD. And technically speaking, you could have called it AXD or AYD. But we'll call it ABD. And that arc has the measure of the first one plus the measure of the second one. The measure of arc AXB, this measure right here, whatever this angle is, plus the measure of arc BYD. Pretty straightforward. Okay, so we're going to make a statement and then prove it to finish up this video. Prove that two chords of a circle are congruent if and only if they subtend arcs of equal measure. Remember what subtending arcs means. Well, I'd have to draw chords in this previous example, so we'll end up drawing them right here. I've already labeled some points on these two circles, A, B, C, and D. So let A, B, and C, D be two chords of a circle. So A, B, and C, D are two chords of a circle. We're going to prove that if the lengths of those chords are equal, well, they are equal, if and only if the arcs have equal measure as well. The segments, the chords, are congruent if and only if the arcs that they subtend are also equal in measure. Okay, so assume the arcs are minor arcs. For major arcs, the proof would be very similar, but it's easier to draw when we have minor arcs. Okay, we're going to do it this direction first. So we're assuming that the measure of the arcs are equal to each other. So that means that this arc is equal to this arc right there. So somewhere I need to put the center of the circle, call that O. All right, well, what does it mean for the arcs to be the same? By definition, what is the measure of an arc? It is the measure of the angle that subtends that arc. So we know that these two angles are equal to each other because the arcs are equal to each other by assumption. And we also know that that side, that side, that side, and that side are all equal measure because they're all four radiuses of the same circle. So let's formally write this out. The measure of angle AOB is equal to the measure of angle COD, this one, by the definition of an arc. Okay, if the arcs have the same measure, these two angles have the same measure. If these two angles have the same measure, the arc that they subtend have the same measure. All right, so the second thing we're going to say is what we've already put the notches on those sides. I'm going to say that OA is equal to OB is equal to OC is equal to OD. Okay, and we know why that's true. They're all radii of the same circle. And what does that tell us? It tells us that, I could call this step 3, but I'll just write it right here. Triangle AOB is congruent to triangle DOC, or COD. Either way is actually fine. COD. Why is that? Because of side angle side. Side angle side. Well, since those two triangles are congruent to each other, we know AB is equal to CD because they're corresponding parts. Corresponding parts of congruent figures are congruent. So we're halfway done with the proof. We did the right to left. For the second one, we're going to assume this is true to prove this is true. Okay, we went from this implies this. Now we started off with this implies this. Now we're going to prove this implies this. So let's assume that AB equals CD. And I'll go ahead and say why to prove that the measure of arc AB is equal to the measure of arc CD. All right, so we know by assumption that AB is congruent to CD. So let's put a little notch through each of them like that to show that they are the same length. And all we need to do is prove that the arcs are equal to each other, the measures of the arcs. All right, well, I'm basically going to repeat something from above, repeat number 2. We know that OA equals OB equals OC equals OD. And why do we know that? Because every one of those line segments is the radius of the same circle. Okay, so that's the reason I'm not writing it down. And let's see, therefore, that implies that triangle AOB is congruent to triangle COD. This time it's a different reason. It's not SAS. We don't have any angles that we know are the same, but we have side, side, side. And that's the definition of a triangle. If you know the 3 sides and another triangle has the same 3 sides, they are congruent to each other. So I'll put side, side, side. Okay, so therefore, by corresponding parts, we know that angle AOB, that's O, AOB, is congruent to angle COD, this one right here. Those angles are the same. And that's by, again, corresponding parts of congruent figures are congruent. Therefore, we know that the measure of arc AB, the measure of this arc, by definition, is the measure of this angle, is equal to the measure of arc CD, which is the measure of this angle. Since we know those two angles are the same, we know the measures of the two arcs are the same. I'll even put by definition of an arc. And that's the end of the proof.